and we'll get going with the tail end of chapter 9. Now, we left off talking about exceptions to the octet rule. We did lots of that stuff yesterday in lab. Hopefully you're feeling more confident about your Lewis structures and, deciding whether or not a molecule has resonance, assigning those formal charges, and, if there is resonance, is one of these resonance structures better than the rest based on the formal charge? If it's an expanded octet, can I use those formal charges to determine whether or not we're going to form multiple bonds to expand that octet, that kind of thing. So hopefully yesterday's practice was good for you. Now, we talked in chapter 6 about enthalpy, and we spent a good time sort of calculating the enthalpy of a reaction based on the enthalpy of formation for that molecule. The issues arise when we have a brand new molecule or somebody synthesized something new and different, and there's no enthalpy of formation for that compound yet available. One of the things that we can do is use bond enthalpy, so the energy of a single chemical bond, and essentially just add up all the chemical bonds for the products and all the chemical bonds for the reactants and find out what that difference in energy is. And so we call that bond enthalpy. Now, when we look at the bond enthalpy table, this is just for a single bond, and it's got to be in the gas phase. Again, gas phase is just sort of the easiest way to make it even across all compounds. And so you'll notice here that, if we look at some of these, the hydrogen bond here at 436 at the top of our table. Some other ones, let's see, a carbon-carbon single bond at 347, a carbon-iodine bond at 240. So you kind of get the idea of a single bond is somewhere between, say, 200 and 500 kilojoules per mole. And that's about the right range. So 200 to 500 kilojoules per mole for a single bond. Now we've got the table in front of us, so hopefully it's easy to see that when we jump up to double bonds, those double bonds tend to be stronger, right? And that makes perfect sense. We know that in a double bond, instead of just sharing one pair of electrons, we're now sharing two pairs of electrons. And so it takes a little bit more energy for us to pull apart molecules that are sharing two pairs of electrons than it does molecules sharing just a single pair of electrons. And so when we look at double bonded compounds, like let's say we have a carbon-carbon bond here, right? There's 620. Carbon-nitrogen bond, 615. Carbon-oxygen bond, 745. Oxygen-sulfur bond, 469. And so it looks like, a rough estimate is anywhere between 500 and 800 kilojoules per mole for a double bond, right? And so it's not exactly double in terms of the energy, but it is certainly larger. And then for a triple bond, there's not a whole lot of those on our table, but there's a carbon-nitrogen triple bond at 891, carbon-oxygen triple bond at almost 1100, and then a nitrogen-nitrogen triple bond at 950. And so we're looking at 900 to 1100 kilojoules per mole for a triple. And so the general trend is that the more electrons that you share, the stronger that bond is, the more energy it takes for that bond to be broken. And so as we increase the bond order, which we talked about yesterday, right, we increase the bond enthalpy as well. When we talk about an increase in bond enthalpy, we call that an increase in bond strength. That's another way of talking about this. Bond strength. right? So a triple bond is a stronger bond than a single bond. Now let's think just a second about bond length. Which do you think is going to be a shorter bond? A single bond that shares 2 electrons, or a triple bond that shares 6 electrons?
Triple.
Yeah, a triple bond is shorter than a single bond, and that mostly comes from the fact that in order for those electrons to overlap, remember those electrons are in orbitals, and in order for us to share electrons, orbitals have to overlap. In order to get overlap for not just 2 electrons, but for 6 electrons, those 2 atoms have to be much closer together. And so again, as we increase bond order, we decrease this bond length. Right? We're decreasing the distance between those 2 atoms. All right. There's one thing that I want to highlight here before I move off this slide. The carbon-oxygen double bond, well, all this table is just average bond enthalpies, right? It's not exactly, if we look at HO here, oops, I wanted highlighter, there we go. If we look at hydrogen and oxygen here, it's not 460 for every single hydrogen oxygen bond that you find out there. It's a little bit different for water, it's a little bit different for alcohol, it's a little bit different for amino acids, but on average, it's 460 kilojoules per mole. If we look at the carbon-oxygen double bond, it's 745 kilojoules per mole, and that's okay, but we are going to use carbon dioxide a whole heck of a lot. And it gives us, down here at the bottom, that carbon dioxide has a bond enthalpy of almost 800, 799 kilojoules per mole down here at the bottom. That's so far different from the average that we have to make sure we use the one that's specific for CO2 when we do those calculations. Okay. I just wanted to point that out because we are going to do some practice here. And I think one of the ones that we're going to do is involve CO2. So, okay. All right. In chapter 6, when we talked about enthalpies of formation, we did the enthalpy of formation of all the products minus the enthalpy of formation of all the reactants. In other words, all the energy that was released, forming the products, minus the energy that was put in, forming the reactants. We're going to do the same thing. The energy that the change in energy is our energy input, right? So breaking all these bonds minus the energy that is released, and so that's forming bonds. When we talk about reactants and products, rather than energy input and breaking or forming bonds, in this diagram, it shows us that we take the reactants and we go from the reactants to the individual atoms and then back down to form products. And so because atoms is our middle ground, breaking all those bonds is the energy that we have to add to the reactants, not to the products. And so really, I think about this as the bond enthalpy, I'm going to abbreviate that BE, of the reactants, okay, minus the bond enthalpy for the products. Right? Now, we were so accustomed in chapter 6 to do products minus reactants. Now we're going to be doing reactants minus products, but it all has to do on where is that energy going in and where's that energy coming out. Okay. All right. So before we do an example, for figure A here, where our reactants are lower in energy than our product, is this one endothermic or exothermic?
Endothermic?
I'm sorry, you're gonna have to be a little bit louder.
Is it endothermic?
Endo. Yeah, absolutely, right? We have to put in a lot more energy to get up to those individual atoms, and we don't get all that energy back out. And so this one is endothermic, right? Our delta H here is positive, and that makes this one exothermic. We get more energy out when we make those products than we put in when we get those reactants. And so there, our delta H is negative. Okay. All right, so let's do an example. The reaction of H2 plus Cl2 goes to 2HCl. I've pulled the bond enthalpies from the table for us, so that's a little bit easier. And here, in this particular example, it goes ahead and it gives us those structures, right? This is nice. The reason we do Lewis structures before bond enthalpy is because we have to know what kind of bonds are in that molecule in order to know what the bond enthalpy should be, right? That's why we have to know something about the correct structure, whether it's has some resonance, whether it's got an expanded octet and therefore multiple bonds versus single bonds. And so we have to know our Lewis structures first before we can do some of these problems. And so our delta H is the bond enthalpy, equals the bond enthalpy of our reactants, right, minus the bond enthalpy of our products. And so delta H is, well, we're breaking a molecule of H2. It's just one. I'm going to put that one there just so that we follow it. And H2 is 436.4 kilojoules per mole. On the other reactant we have is 1 mole of chlorine. And chlorine is 242.7 kilojoules per mole. And then we subtract the bond enthalpy of the products. How many moles of HCl are we making?
2.
2. And so we have 2 moles of HCl bonds. 2 moles of bonds. We're going to come back to that in the next example. But each mole of bonds is 431.9 kilojoules. And so let's plug this into our calculator. 436.4 plus 242.7. I got negative 184.7 kilojoules per mole. Hopefully you got something similar. Okay. Again, we just have to figure out all of the bonds that are breaking minus all the bonds that are forming. Right? So again, this is bonds that are broken and bonds that are formed. Right? We had to break this bond and this bond so that the hydrogen and the chlorine could bond together once and twice to form these new bonds. Okay. So let's do another one. Estimate the enthalpy change for the combustion of hydrogen gas. Okay. So hydrogen gas, H2, combustion. What does a combustion reaction look like?
plus O2.
Yeah, we have to add some oxygen. And what are we going to form? Combustion always forms.
Carbon dioxide and water.
Yeah, carbon dioxide, water, that's what we think of. Do we have a source of carbon in our reactants? No. So then the only thing we're going to form is water, right? Kind of a tricky one because we're used to having some carbon dioxide when we talk about combustion, right? As a quick aside, this is one of the reasons why we're interested in hydrogen as a fuel, because when you burn it, you still get all that energy out, but you don't have any carbon dioxide greenhouse gas. Okay. Is this equation balanced?
No.
No, it's not. Yeah. So we need to throw up some coefficients here. 2 moles of hydrogen will give us 2 moles of water, and we just need 1 mole of O2. Okay. All right. I'm going to give you just a minute to work on that one. All right. So hopefully you have delta H is equal to 2 times 300, oh, sorry, 436.4 plus 1 times 498.7 minus, how many moles of OH bonds do we have?
Two.
So there's 2 moles of water. How many OH bonds are in each water molecule?
2.
2. So how many moles of OH bonds do we have?
4.
4.
4, yeah. So this is one of those times when we have to think about counting individual bonds rather than counting our molecules, right? And each of those is 460 kilojoules per mole. So that's going to change our delta H and change it fairly substantially, right? 2 times 436.4 plus 498.7 is 1371.5 minus 4 times 460. 1640. Negative 468.5 kilojoules per mole. Right? And so if we didn't include those, if we put a 2 instead of a 4 there, it'd be a positive number. And hopefully we know that combustion, generally speaking, is not endothermic, but exothermic. And so we should get a negative value for our delta H. Did I do my calculations correctly? Is that one good? I think so. Okay. All right. I've added one more example for octane. So this is not in your notes, but this is a very similar example. And I'm not going to do the whole thing with you, but I'm going to get you started and then you can work on it on your own. So when we look at the combustion of octane, well, first, we have to remember all the way back to chapter 2. I know it's been forever and a day, but we have to remember what octane is, right? That's one of those alkanes. And so octane, how many carbons do you think octane has?
8.
8 carbons for sure. And all the alkanes had a certain formula. If there were NCs, does anybody remember how many hydrogens there were?
N plus 2.
Not quite N plus 2.
2N plus 2.
There we go, 2N plus 2. So every carbon takes 2 hydrogens, and then the carbons on the end each take an extra. And so it's C8H18 according to that formula. And it's going to react with oxygen to form CO2 and H2O. We need to balance this bad boy. So we have 8 carbons. We need 8 CO2s. We have 18 hydrogens. That gives us 9 water molecules. That gives us 8 times 2 is 16 plus 9. That's 25 oxygens. Instead of multiplying everything by 2, I'm just going to do 25 halves here. If that freaks you out, feel free to multiply through by 2 and get some whole numbers. Right. So we need the Lewis structure for octane. We need the Lewis structure for O2. We know that it's just a double bonded O. The Lewis structure for CO2. And remember, the CO2 is a funny one. The C double bonded O in CO2 is not 745 like it says on the table, but 799 kilojoules per mole. And then water, okay? I'm going to leave us there, and it's good practice if you work through that one, okay? Now, octane is one of the major components in gasoline, and so this should be a very negative number. Okay? So make sure you take into account all those carbon-carbon bonds, all those carbon-hydrogen bonds, and then all of the bonds in carbon dioxide and water, okay? Monday in class, I'll give you the answer to this one in case you do it over the weekend. Okay. So I'm going to stop there for chapter 9. The chapter 10 slides are on Moodle. If you haven't pulled those off yet, go ahead and do that. We are going to get started in chapter 10 real quick. Just doing the first little, the first few slides. Okay. Right. Okay, so chapter 9 was all about chemical bonding. Not only did we talk about ionic bonding there at the beginning, but we spent a whole heck of a lot of time talking about covalent bonding and how those atoms share electrons, what they look like in terms of their electron arrangements, how they bond. So there's a double bond, a single bond. We're having all those extra electrons. They're in lone pairs. Right? We spent all of this week going over that. And this is good. This is stuff that we're interested in as scientists. How do things bond together? How do they hold together? But more applicable than that is, what shape do they take on after they've bonded? Right? How do we take that Lewis structure and convert it into some three-dimensional shape that then makes sense? This is important for things like enzymes. Oops. If we look here at enzymes, they have that whole lock and key kind of mechanism where the active site is exactly the right size and shape for whatever that substrate is for that enzyme. And so this is just one of the reasons that we need to know the shape of our molecules, even really big molecules like proteins. And you can even see maybe a little DNA wiggle in there. I don't know. I don't know exactly what this image is. It's out of our textbook. Okay. And so that whole field of looking at the shape of molecules is called molecular geometry, right? That makes sense. We're going to look at the geometry of our molecules, and it's dictated by this valence shell electron pair repulsion model. And so some people say VSEPR, some people say VSEPR. It doesn't really matter to me. I'll probably go back and forth between the two. But what this does is, let's sort of break down that name. We're talking about valence shell, right? That makes sense because that's all we paid attention to when we drew Lewis structures. Electron pair repulsion. And so we know that electrons are negatively charged. We know that they're in pairs because they're in different orbitals, and so they pair up in the orbitals. But we also know that negative charges don't really love to be next to one another, and so those orbitals are going to spread out in space as much as possible to get away from other negatively charged electrons. But this is only true for those valence shell electrons. And so these valence electron pairs, either in bonds or in lone pairs, are going to repel away from each other as far apart as they can around some central atom. And the geometry that arises is this molecular geometry. And so this VSEPR theory helps us predict what the geometry is going to be around some central electron. And so the terminology that we're going to use all throughout chapter 10, A is going to be our central atom. Okay. Anytime we see a B, that's going to be a bonded atom, right? So some atom that's bonded to our central atom. And then an E is a lone pair of electrons. So today, in the time we have remaining, we're just going to go through the broad category of geometries when we don't have any lone pairs and the central atom has as many bonds as it can take. Okay. And so the very simplest one would be one central atom with two bonded atoms around it. Okay. Well, let me back up a minute. The very simplest one would be one atom bonded with one other atom. But if you have 2 points, that's always going to be a straight line. And so the geometry of a 2-atom system is always going to be, linear. There's no other way to do that. They're always going to be in a straight line from one to another. And so we start with 3 atoms, and the simplest way to have 3 atoms is one center atom with 2 bonded atoms to it. And so we have 2 atoms bonded to the central atom. That's what the B is. We have no E's in this formula, and so there's 0 lone pairs. And if we have these 3 atoms, again, the way to arrange these atoms so that the two electron pairs, those two bonds, are as far apart from one another as possible, is still in a linear arrangement, right? So they're still going to be as far away from each other as possible. And the easiest way to do that is to be exactly opposite one another around that central atom. And so the electron pairs are linear, right? And if it's linear, what's that bond angle? If we were to measure this bond angle, how many degrees would that be?
180.
180.
Absolutely. If it's linear, it better be 180 degrees. For this first little bit of this, we're going to make a table here. For the first little bit of this VSEPR, the electron pairs and the molecular geometry are going to be exactly the same because we don't have any lone pairs. When we talk about molecular geometry, we're talking about just the atoms, not taking into account the lone pairs. And so when we come back to this on Monday, we'll find some differences between the arrangement of the electron pairs that sometimes we call the electronic geometry. And the molecular geometry. But for today, they're going to be exactly the same. Okay. So a good example of this, something that only makes two bonds, well, that's going to be a reduced, that's less than 8 electrons, that's less than an octet. And so beryllium chloride, remember, he is okay having that, having fewer than 8 electrons. And so beryllium chloride is a perfect example of one of these molecules that has a linear structure. Okay. Again, that bond angle is 180 degrees because those electron groups want to be as far away from one another as possible. Okay. All right, that one pretty straightforward. If we move up to the next, to adding one more electron in, right? Well, then it's going to be AB3. So I've got 3 electrons, sorry, 3 electron groups that are all bonds. There's no lone pairs. And so if we have our central atom A, the best way for those to get separated from one another in 3-dimensional space is to just be sort of the points of a triangle. And so we're going to have a B up top, a B over here, and a B over here. And those are going to kind of form a triangle. Right? And if we have this triangle and all of our atoms are the same, right? All our B's are the same. What's this bond angle going to be?
120.
120 degrees, yeah. So if the whole thing is 360 and we're splitting it into thirds, we end up with 120 degrees between those atoms. Okay. Now, because we're talking about a triangle, this is all in the same plane, right? We can write all of these atoms on the same sheet of paper without having to figure out how to bend the paper out of the plane. And so all of these atoms are going to be in one plane of space. And so we call this trigonal for the triangular shape planar because it's in one plane. And so of course the molecular geometry matches trigonal planar. I got to grad school and one of my professors started calling it trigonal. And that's not what I do. But if that's how you learned it in high school, I am okay with trigonal planar. It's just weird to me. Okay. So again, we've only got 3 bonds. We've only got 3 electron groups. That's only 6 electrons. So we must have some compound that's okay with that. Turns out boron trifluoride is that compound. Now, I'm going to take us back a step because when we had boron trifluoride as an example for those reduced octets, we drew it like this, right? And while this might have been okay for chapter 9, this is not okay for chapter 10. The reason is we know now that that's not how those atoms are truly arranged in space, right? Those atoms are in that trigonal arrangement. Now, do I care if the point of your triangle points up or left or right? No, I don't care which direction your triangle points, as long as you have it in the rough geometry. I also don't care if they're exactly 120 degrees, right? I just don't want it to be this T-shaped thing like we saw over here. And so there's our Lewis structure for boron trifluoride. Again, we know that all of these bond angles are 120 degrees from that triangular structure. Okay. Any questions so far about this VSEPR theory and the stuff building up to it? Okay. So now we're adding yet another electron pair, another bond, and so we come to AB4. We've got 4 bonded atoms, no lone pairs. We cannot put, well, the best structure for these 4 electron groups in 3-dimensional space is not to just make a cross, right? It's to distort that cross a little bit. And we do that in something called a tetrahedron. And so the shape is tetrahedral. And I'm going to do my best to draw this. Okay. So if A is in our middle here, we've got a B coming up and a B coming out. Now, the way that this works is that you've got those 3 atoms that are in a plane, and then one atom comes towards the viewer, and the other atom, is going away from the viewer. In chemistry, the way we represent that is by having sort of a solid wedge, right? And this is our B atom that's coming out at us. I'm going to try to make it just a little bit bigger so it looks like it's coming at us. And then we draw a dash to show that there's a B that goes back into the board. I'm going to draw him a little bit smaller so it shows that he's a little bit farther away. Right? I'm going to have to go to campus at some point this weekend so I can get my model kit. My model kit is sitting in my office, and it would be much easier to show you these things using a model kit. But that's how we represent the 3-dimensionality of the arrangement of these atoms on a 2-dimensional flat surface. Okay. If we were to hold this molecule up and A and 2 B's were in a plane, the B coming forward and the B going backward would be directly behind one another. Okay. And so we can't draw one bond to them and keep the geometry accurate because one's in front and one's in back. And so we draw that wedge and that dash so that we can tell that those are slightly shifted, one coming in front of the page, one is behind the page. Now this angle here is now it's in 3-dimensional space, and it's it turns out that the best angle for this is 109.5 degrees. Right? There are many books, including our textbook, that say this is about 110 degrees, and they just leave it at that. Right? We lose 2 whole sig figs, but we put it at 110 degrees. Okay. Well, now that we're up to 4 bonds, we're happy we have our octet. And so there are a whole heck of a lot of compounds that have this tetrahedral electron pair arrangement, right? Again, the reason being that this is where we start having that full octet, and we don't have an expanded octet, right? 8 electrons is the most that lots of atoms want. And so it turns out that we use tetrahedral geometry, or we find tetrahedral geometry a whole lot in the real world. Okay. All right. So the simplest molecule, or one of the simplest molecules with this geometry, would be methane. And so again, we previously would draw our Lewis structure for methane, CH4. That's the second time today we've used those alkane namings. If you need to go back to chapter 2 and review those, do so. So we would have said, okay, CH4, this is the Lewis structure. Not anymore, right? Not anymore, because we know that the Lewis structure for CH4 should take into account the real geometry of those atoms. And so, 3 of our atoms are in the plane. We don't need any wedges or dashes for them. We're going to put a wedge out to the one that is coming out at us out of the plane, and we're going to do a dash back to the one that's behind the carbon that's going into the plane. Okay. Our textbook does a good job at drawing this dashed wedge with the wedge part closest to your face and the dashed part farther away. There are some other sources that will draw it the exact opposite. Even though we know that it's going away, they draw it with the big wedge end closer to the bonded atom and the small wedge end closer to the central atom. It really doesn't matter to me which way you do it, as long as you have this dashed wedge that shows going behind the plane of the molecule and the solid wedge coming out of the plane of the molecule. All right. So that was with 4 bonded atoms. So now move up to 5 bonded atoms with no lone pairs. We know that this is now an expanded octet situation. And so the way that this looks is that we have our A in the middle. And to get 5 atoms spread out as far as possible in space, turns out that you have 2 that are linear with our central atom. And then you sort of form a ring of 3 around the middle. And so you have A with a B at the top and a B at the bottom. And then you have a B out to the side. And again, we're going to have to use our wedges and dashes because we have this sort of ring of 3. If one of them is in plane with our central atom, one of them's coming forward and one of them's going backwards. And so we have a B coming out. And we have a B going back. Maybe I should try real hard to draw this one real big and that one kind of small. Okay. We call this trigonal because those 3 in the middle, let me use blue for the middle ones. Those 3 in the middle form a triangle. Right? And so that's where our trigonal comes from. And if we kind of try to connect the dots here, we've got a pyramid on top, but that pyramid has a triangular base. And we've got a pyramid on the bottom. Right? And so we call it trigonal bipyramidal because we've got a pyramid on top and a pyramid on bottom. Those are trigonal pyramids because the base there is that triangle in the middle. Again, some people say trigonal bipyramidal, which blows my mind, but however you want to say it is okay. Now, because we've got this triangle in the middle. We've seen a planar triangle before, and we know that this angle is what?
120.
120. Yep. We call this triangular circle the equatorial positions. If we think about this as a globe, right? The top and bottom B form our axis, and those three in that triangular position form our equator. And so we call these equatorial. And so the equatorial bond angle is 120. Now, between the equator and we call these top and bottom ones the axial, right? Because they form that axis down the middle of the molecule. Between the axial and the equatorial, right? That's his closest neighbor. What's that bond angle? Might be hard to see.
90?
Yeah, it's a 90-degree angle, because if you have your axis and you have your equator, those are 90 degrees from one another. Okay. All right, we're running out of time, so we're going to stop there for today. We'll come back and we'll talk about an example of trigonal bipyramidal, and then the last main geometry, which is octahedral. We'll do that on Monday. All right, I hope you have a great weekend, and let me know if you have any questions.
Thank you.